It will take centuries to terraform Mars. Mars is a gigantic planet, roughly on the order of half the size of the planet Earth.
In a significant discovery, astronomers have transformed our perception of Mars from an empty, desolate space to a planet with a mysterious core. Contrary to expectations, Mars had a history of warmth, liquid water, and the potential to sustain life. This breakthrough resulted from the meticulous investigations carried out by the Insight Rover, which extensively explored the planet's interior, revealing its seismic activity. Following a challenging 5-year journey, Insight has granted scientists a comprehensive understanding of Mars' puzzling core, fulfilling our long-standing curiosity about it. Armed with this newfound knowledge, the prospect of eventually inhabiting Mars edges closer to reality. So how does Mars' core differ from Earth's? And how did Insight unveil this core? And importantly, what insights does Mikio Kaku offer about this discovery? Let's delve into the details. To truly grasp the significance of Insight's accomplishments on Mars, it's essential to delve into how scientists unraveled the mystery of Earth's core over a century ago. The key to this understanding lies in the study of seismic waves, shock waves that traverse the depths of our planet. These waves can originate from natural occurrences like earthquakes or controlled explosions created by humans. By scrutinizing how these waves behave as they traverse different materials, scientists can infer the properties of those materials. Just as light waves interact with objects by being transmitted, reflected, absorbed, refracted, polarized, diffracted, or scattered, seismic waves also alter their behavior when encountering different substances. Seismic waves mainly manifest in two forms, P waves and S waves. P waves, also termed primary waves, are compressional waves that cause rocks to vibrate in the same direction as the wave's movement. They stand as the quickest seismic waves, reaching the earthquake's center first. Conversely, S waves, or secondary waves, are shear waves that induce rocks to vibrate perpendicular to the wave's movement. They move at approximately 60% of the speed of P waves, typically arriving after the P waves have passed. In 1806, scientists made a significant finding. Seismic waves travel more slowly through Earth's core compared to other regions. They also noted an interesting phenomenon. S waves couldn't penetrate the core, while P waves could, albeit with a change in direction at the core's boundary. Based on these observations, scientists inferred that Earth's outer core exists in a liquid state, surrounded by the solid mantle. Further investigations deepened our understanding of Earth's core. In 1936, researchers observed seismic waves reflecting off the inner core, indicating a shift from a liquid to a solid state. These pivotal discoveries, stemming from meticulous seismic studies, significantly contributed to our comprehension of the intricate layers constituting Earth's core. Now let's move forward almost a century to explore Mars' interior, where scientists have employed similar seismic techniques to unveil remarkable findings. In 2018, the Mars rover Insight embarked on a mission to thoroughly analyze Mars' crust, mantle, and core. An essential aspect of this mission was deploying a seismometer named the seismic experiment for interior structure on the Martian surface. This tool was specifically crafted to gauge seismic activity and generate precise 3D models of Mars' interior. Throughout its active 4-year span, the InSight mission made a noteworthy discovery on Mars. In 2021, two significant events occurred on the opposite side of the planet, grabbing scientists' attention. Firstly, InSight recorded a substantial Marsquake, surpassing any previously observed seismic activity. Secondly, a meteorite impact induced a seismic disturbance. These incidents occurred far from InSight's location, offering the unique opportunity to analyze the seismic waves traversing around and through Mars, providing researchers an unparalleled glimpse into the Martian core. Scientists compared the travel times of these seismic waves through the core with those confined within the Martian mantle. By integrating this data with other seismic and geophysical measurements, they estimated the density and compressibility of the materials encountered by the waves. Surprisingly, the findings unveiled that Mars' core is consistently liquid, in contrast to Earth's core, which is likely characterized by a solid inner core surrounded by a liquid outer core, potentially with a denser innermost core. Further investigations revealed that Mars' core contains a notable amount of lighter elements dispersed within it. On average, these elements contribute almost a fifth of the planet's weight, with sulfur being the most prevalent, accompanied by smaller amounts of oxygen, carbon, and hydrogen. This unexpected composition emphasizes the distinctive geological structure of Mars. These discoveries suggest that Mars' core exhibits lower density and greater compressibility in comparison to Earth's. On Earth, the geodynamo, responsible for generating the magnetic field, is fueled by activity within the core. In simpler terms, heat travels from the inner core to the outer core, creating currents in the conductive fluid within the mantle. As the planet rotates, these currents may twist, giving rise to a magnetic field. This magnetic field then interacts with fluid motion, resulting in a secondary magnetic field referred to as the dynamo effect. This mechanism serves as the foundation for Earth's self-sustaining magnetic field. Previous studies on Martian magnetism indicated that the presence of lighter elements in the core might have played a significant role in the loss of its dynamo and subsequent magnetic field. A clearer understanding of Mars' core composition enables scientists to reconstruct the planet's history more accurately. A planet's core characteristics offer valuable insights into its formation and evolutionary history. Earth's distinctive core composition enables the generation of a magnetic field, protecting us from solar winds, preserving our planet's water, and supporting life. In contrast, Mars' core lacks the ability to create this protective shield, rendering it inhospitable for known life forms. These investigations not only aid in identifying potentially habitable exoplanets, but also deepen our understanding of the diverse ways planets can form, grow, and evolve over time, even when originating from similar materials around the same star. The Insight mission, concluding in December 2022, significantly impacted our comprehension of planetary formation and evolution. Throughout its 4-year exploration of Mars, it gathered high-quality data, offering valuable insights into the planet. This mission underscores the significance of scientific exploration and discovery. In a recent finding, astronomers revealed an intriguing aspect of Earth's magnetic field. They observed that a weak spot in the magnetic field is deteriorating, resulting in a specific crack on our planet. If you haven't caught up on this development, it's advisable to do so, given its significance. Beyond shedding light on Mars' core, the Insight mission also unveiled other captivating discoveries about the planet. It identified over 1,300 seismic events, with more than 50 displaying clear signals that aided in pinpointing their location. Cerberus Fossae, a region indicating recent volcanic activity on Mars, exhibited the highest number of seismic events with notable quality. These observations imply that Mars has undergone geological activity within the last 2 million years. The most significant seismic occurrences were noted in mid-2021, with Insight detecting all 6 of the largest events since then. The most recent event in May 2022, registering a magnitude of 5, induced planetary shaking for a minimum of 6 hours, revealing the dynamic nature of Mars' interior. Insight's data also shed light on Mars's major layers: the crust, mantle, and core. Surprisingly, the crust beneath Insight proved thinner than anticipated, measuring approximately 15 to 25 miles in thickness and comprising 3 layers. The uppermost crust layer is around 6.2 miles thick and less dense compared to the lower crust. Another unexpected discovery was the larger than previously thought size of Mars's core, boasting a radius of about 1,120 miles. The core's lower density suggests a mix of lighter elements with molten iron, elucidating why the core maintains a molten state despite gradual cooling by analyzing seismic waves traveling from the upper mantle to the surface. The Insight mission has uncovered significant findings about Mars. It unveiled the existence of a robust and chilly outer shell known as the lithosphere, measuring around 310 miles in thickness. This lithosphere distinguishes Mars from Earth as it overlays a relatively cooler mantle. Comprehending Mars's layer composition, structure, and the mechanisms of heat dissipation has provided valuable insights into the planet's geological past and its potential habitability. Insight's discoveries have greatly enhanced our understanding of Mars's surface conditions and its progression as a potentially habitable celestial body. Beyond delving into Mars' interior, the mission has gathered crucial data regarding the atmosphere and weather. Utilizing its weather sensors, Insight detected numerous passing dust devils. Even though the mission's cameras didn't capture direct images of these dust devils, Insight's pressure sensor recorded pressure changes induced by these whirlwinds. The seismometer also identified surface movements triggered by the dust devils, resembling the effect of a substantial vacuum cleaner tugging at the surface. So thanks for watching. If you enjoyed watching this video, give it a thumbs up and subscribe for more.